All right, so we're going to finish up this chapter by talking about another strange characteristic or property of quantum mechanics called the Heisenberg uncertainty principle. So in order to do that, we need to review single slit diffraction. So as you recall, when you shine light through a thin slit, you see this interference pattern. And we discussed that in gory detail some time ago. And here, same thing, right? So there's the thin slit, there's the interference pattern, and we figured out quite a while ago that this central max, the width, is 2L wavelength over the slit width. All right. Now what we want to do, we want to do the single slit diffraction experiment, but this time, instead of using light, we're going to use a narrow beam of electrons. And so it's along the x-axis. And so we're just going to use an electron beam. So pretty much all the electrons have, nearly the same direction and nearly the same speed. Now, what does that mean? Well, remember, lambda equals h over p, which is h over mv. So they pretty much, most of them have the same de Broglie wavelength. All right, so you do that experiment with the electrons, and ta-da! Are you surprised? You see the central max, and then you see this diffraction pattern. So it's the same single slit diffraction that that we saw with light. But this time it's electrons. So what does that imply? It implies that electrons, that we think are particles, are actually acting like waves, because this is a wave phenomena. All right, that's cool. So waves, so particles act like waves. All right, we already discussed that in gory detail. So now we want to interpret this, though, in terms of particles. So basically, we're going to, look at the data. Okay, look at the data. All right. Now, the fact that you get a diffraction pattern indicates that not all of the electrons follow the same path. Now, they pretty much had the same initial state of motion, but look, most of them fall here, but some fall here, some fall here, some fall here, And so what does that say? It says that you cannot predict where a single electron is going to fall. You can say that most are going to fall here, but you don't have a clue where each electron is going to go, all right? So all you can really say, you can say the probability of an electron landing here is high, and so forth and so on. All I can talk about is probabilities. Now that's weird, right? Did we ever talk about probabilities in classical mechanics? Of course not. Well, guess what? In quantum mechanics, all you can do is measure probabilities. All right, so that's weird, right? That's kind of different. Second of all, what we're going to see is that there are fundamental uncertainties in the position and the momentum of each particle. And they're related, and that's what we want to get. We want to get the relationship that shows how the uncertainty in position and the uncertainty in momentum are related. So here we go. Here we go. Uh-oh. Come on. Wow, that's nice. 1 second. Yes. So always have a backup. Okay. So here we go. The electron beam, single slit, central max, and all that, right? Okay. So the slit width here, the A, that represents the uncertainty in the Y. This is the Y. This is the X. All right. So this A represents the uncertainty in the Y. In other words, where the electron actually is, right? We don't know exactly where it is. Could be here, could be here, could be here. We don't know, all right? Okay, so that kind of makes sense, right? Okay, so there's your delta Y, right? Somewhere along here where there's an electron. Now, if there's an uncertainty in the position, delta y, you know, there has to be an uncertainty in the y component of the momentum, right? You know, I mean, we don't have it. We don't know. I mean, here's px, but I mean, if the electron is going like this, you know, this is p, right? So there's px and here's py, and so, you know, if there's a uncertainty in the delta in the y, there's going to be this delta py. Okay. Okay. So what do we want to do? What do we want to do? We want to reduce this momentum, this py. Okay, we want to get this really, really small. In other words, we want to shrink this central max, right? Because we want to get a small, small, small delta py. Okay, so question for you. Here's the equation for the width. We want to shrink it, right? The width represents the delta py. Well, actually, the width is twice that, right? Okay, so how can we shrink this? Look at this equation. You know, we're not going to change the wavelength. We're not going to change the L. So what can we change to shrink this width, to shrink delta py? What can we change? Well, it's sort of obvious, right? You look at that. If we want this to be small, we really can't touch anything here. We have to make A large, okay? So to shrink delta py, we have to increase A. Okay, whatever, you know, we can do that. All right? Okay. But again, think of what we just said. In order to shrink this, we have to increase this. Oh, gee. All right? Now let's ask the second. Okay, now let's go back. What if we want to shrink this? What if we want to shrink delta y? In other words, we want to shrink A. How is that going to affect delta py? Is that going to affect the central max? Well, you know, look at the equation, right? If we shrink our delta y, we decrease delta y, we decrease A, this is going to get smaller. What's it going to do to the width? What's it going to do to the delta py? Well, if A gets smaller and smaller, the width gets wider, so we increase our width, we increase our delta py. Wow, so what did we just see? Well, we just saw the first thing we did. So if we decrease delta py, what happens? Our delta y increases. Then what we saw is if we decrease our delta y, then delta py increases. So what's the bottom line? You can't shrink both of them, okay? You can't shrink both of them. Bummer! So that's, here's the equation. So in other words, what we're saying is delta py times delta y is a constant, all right? That's the equation that describes this. So this is the uncertainty in the y momentum. This is the uncertainty in the y position. You multiply those together, and it's a constant. So an exact derivation, which we're not going to go through, shows you this. So delta py times delta y is greater or equal to h, remember, Planck's constant, that super tiny number, divided by 4 pi. Okay, now remember, h, come on, it's 6.67 times 10 minus 34 joules seconds. It's super, super, super tiny. So you might say, well, who cares? You know, I mean, it's so small, who really cares? Well, hold on, you'll see. By the way, there's nothing special about the y direction or the x direction. You know, you can put x if you want, you can put y as you want, it doesn't really matter. This is still, you get the same equation. All right, now let's pause for a minute and look at that, and let's restate what it means. Because of the wave-like nature of matter, our knowledge of the particle is uncertain, okay? We're never going to know exactly where it is. We're never going to know exactly where it is. We're never going to know exactly its momentum. There's always going to be uncertainty, right? And this has nothing to do with how smart we are, what kind of computing power we have, what kind of experimental apparatus we have. This is nature. This is a fundamental law of nature. All right? Okay, and again, it's just due to the wave-like nature of matter. You know, you're never going to know, because I mean, think about it. If you knew this exactly, this would be 0. Well, how can 0 be greater than h over 4 pi? It can't, right? So there's always going to be some uncertainty here, always going to be uncertainty here. If you shrink this, this increases. You shrink that, that increases. There's always going to be fundamental uncertainties. That's crazy, right? Compared to Newtonian mechanics. We have never had anything like that in Newtonian mechanics. Okay, so now let's see why we care. Or maybe I should say, let's see under what circumstances this is important. Because, I mean, do you ever notice this in your everyday world? Of course not. All right, so let's see why. Okay, let's talk about the uncertainty of a dust particle. Okay, a 1 micron diameter dust particle is confined within a 10 micron long box. Can we know with certainty if the particle is at rest? If not, within what range is its velocity likely to be found? Now, do we have to use quantum mechanics for a dust particle? Absolutely not. A dust particle is way too large to worry about quantum physics. We only have to worry about quantum physics when we're talking about things like atoms and things smaller. So we don't expect this to be really important. We don't expect the uncertainty principle to be really important. But you know, you got to do the math to see, right? So let's do it. Okay, so here we go. So delta px delta x greater than h over 4 pi. Okay, now let's just say equals, just to, okay, because we want to get the minimum, you know. So let's say, okay, so, all right. So therefore, what's delta p? It's m delta v, right? We're assuming the mass is, you know, the mass is certain, right? Okay, so therefore we have m delta vx delta x equals h over 4 pi. Now, what are we trying to solve for? It says, can we know with certainty if the particle is at rest? That's velocity. So we want to solve for delta Vx. So therefore, delta Vx equals h over 4 pi m delta x. Okay, now, what's delta x? I mean, all we know is the particle, the dust particle, is confined within the box, right? So, but it's somewhere in the box, all right? So delta x is just the length of the box. So I'm just going to replace this with an L, because it's certainly somewhere within the box. Okay. All right. Now, you're going to have to just trust me. I plugged in all the numbers, and this is approximately 5 times 10 to the minus 15 meters per second. So that's delta V, 5 times 10 to the minus 15 meters per second. Well, remember, we don't know if it's going that way or that way, right? So that's not the final answer. What we have to say then, it's somewhere within a range of 5 times 10 to the minus 15. So that means that, but again, that way or that way. So minus 2.5 times 10 to the minus 15 meters per second. Right? Okay? Because the delta V is 5 times 10 to the minus 15. But again, we don't know if it's going that way or that way. So here, if this is minus 2.5, that's plus 2.5. You know, the range is the 5, you know, times 10 to the minus 15. Okay? Now, I mean, give me a break. What's 2.5 times 10 to the minus 15 meters per second? I mean, if that's not 0, I don't know what is, right? I mean, it's pretty close to 0, okay? So, you know, can you know with certainty if the particle is at rest? Well, no, but close enough, right? This is the range. So the velocity has to be, you know, greater than that or less than that. So it's not exactly 0, but it's really, 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 really close, okay? In fact, I mean, at this speed, all right, at 2.5 times 10 to the minus 15 meters per second, if the dust particle was going that fast, or maybe I should say that slowly, it would take 2,000 years to travel 1 meter. Okay, so it's incredibly slow, all right? So, I mean, yeah, we can't say if it's at rest, but pretty close, right? Okay, so is this a waste of time or what? Total waste of time. I agree, but you got to see, right? So the dust particle, as we kind of already knew, we don't need to do quantum mechanics. We can just do Newtonian and we'll be happy. All right, so what good is this uncertainty principle? Well, come on. Like I said, quantum mechanics is when it should be used when you're talking with small things like atoms or electrons or something like that. So there's the answer. So let's do an electron. And now we expect quantum mechanics to be important. Oh, by the way, why do we even care about position and momentum, Well, what did you learn in classical physics, in Physics 105? If you know an object's position and velocity and the forces acting on it, you know everything there is to know about the particle, right? You'll know what's going to happen to the particle, right? F equals ma. If you know the position, velocity, acceleration, or forces, you can predict what's going to happen to the particle. So it's important. Okay, now we want to do the electron, and we expect this to be important. So what range of velocities might an electron have if confined to a 0.1 nanometer wide region about the size of an atom? So this is a practical problem, right? You have this electron in an atom, and it's confined, right? It's confined to that atom. So we want to see what range of velocities are possible, okay? All right, let's do it. So delta x, delta px, I'll just say equals h over 4 pi. And again, p is m delta v. There, okay? All right, so we want to get delta v. So therefore, delta vx equals h over 4 pi m delta x. And again, we're going to just say that delta x is like, the size of the atom. I should say delta, I'll just say L, all right? L, R, whatever you want to call it, doesn't really matter. Okay, so now you're going to have to just trust me again, plug in the numbers, and it's about equal to 6 times 10 to the 6th meters per second. So that's delta V, but again, we don't know if it's going that way or that way. We're just talking about one dimensions, right? So we just say that minus 3 times 10 to the 6th meters per second, V 3 times 10 to the 6th meters per second. Now, with the dust, it was 10 to the minus 15 meters per second. This is 10 to the 6th meters per second, right? This is 1%, right? Speed of light is 3 times 10 to the 8th meters per second. This is 3 times 10 to the 6th meters per second. This is a tenth of the speed of light. We don't have anything, immense missiles or jets or anything like that, bullets, we don't have anything that can go that fast. We have particles in a particle accelerator, but I mean, this is incredibly fast, right? This is here, let's write it like this. Just to show that it's a tenth of the speed of light, all right? So the uncertainty here is enormous, right? It could be at rest. It could be going at a tenth of the speed of light. I mean, wow, that's incredible. Agree? That's incredible. So there you go. So this is, again, think of classical physics. Classical physics, you just calculate something. Here, what does it say? It says that you cannot, it's fundamentally impossible to know how fast that electron's going. All you can say, it's going within this range. Incredible, right? All right. So there you go. All right, let's keep going. Okay, so there you go, all right. Okay, so let's review. We talked a little bit about X-ray diffraction, and that was used to figure out the structure of crystals, the atomic structure of matter. We talked more about the photon model of light. We went into gory detail about the photoelectric effect and how it was explained by Einstein. We talked a lot about the wave nature of matter, which is completely non-classical, right? We talked about how the wave nature of matter leads to the quantization of energy, completely non-classical, right? The particle can only have certain values of energy. And then we talked about the uncertainty principle, how that limits our knowledge of the states of the particles, right, with the position and the velocity or momentum. Okay, so this is just a quick review. X-ray diffraction, you shoot X-rays in, you see the diffraction patterns, and you can figure out the spacing between the planes of atoms. Pretty cool. The photoelectric effect, instead of heating this thing up to eject the electrons, you just use light, photoelectric effect. The results, increasing the light intensity increases the current because you're ejecting more electrons. There's a threshold frequency. So in other words, I don't care what intensity of light you have. If the light frequency isn't greater than a certain frequency, no electrons are ejected, and the current appears instantaneously. And Einstein explained it. Light comes in chunks. This is the energy of a chunk. You call a chunk a photon. Some people say it's a particle of light. That's kind of weird to say because it acts like a wave, so why call it a particle? But what else are you going to call it, right? The photons can't be divided, just like a piece of dirt. The energy of one photon is delivered to one electron. And this was that incredibly important formula that Einstein predicted. The stopping potential, that's the potential, the voltage where not a single electron reaches this part, right? Or sorry, that part, that part. Okay, and the V-stop only depends on the frequency. That's a straight line, and the data agreed with it. Okay, so photon model of light. So we have the wave model we talked about a long time ago, diffraction, interference, and all that. The ray model, mirrors, lenses. Photon model, light's made out of massless photons. Mass, looks that's important. Travels in a straight line, speed of light in a vacuum. Here's the energy, we already talked about that. Superposition of a large number of photons has the characteristics of a wave. So particle wave. Okay, de Broglie, he said, okay, if light acts like a particle and a wave, everything should. Electrons, protons, buckyballs, whatever. So this is the wavelength of a matter particle, right? This could be the mass of an electron, proton, whatever. Completely crazy classically, but it's real, You do the double slit experiment with electrons, you see the diffraction pattern, so the electrons are acting like waves. Then we did the particle in a box model, and what did we come up with? The particle, since it acts like a wave, can only have certain energies, so we say it's quantized. So this is E1, and this is En, where n is just a 1, 2, 3, 4, 5. And so quantized energy, just like eggs, just like money. Then we did the whole thing with the you shine light through a prism and all that. So this is this is atoms, right? Stationary states and quantized energy. So when an electron orbits an atom, classically, the electron emits light, so it loses energy, so it eventually would smash into the nucleus. Well, that doesn't happen because, we exist, right? It would take like less than a millionth of a second to self-destruct, right? So there have to be stationary states, have to be quantized energy, and we learned that an electron goes from a high energy state to a low energy state by ejecting a photon, goes from a low energy state to a high energy state by absorbing a photon. And we saw that atoms emit and absorb a discrete spectrum, right? Because every element has an energy diagram, certain unique values of energy. So in order for the electron to go to change states, the photon has to have the exact energy between the states. Absorption wavelengths are a subset of the wavelengths in emission. Each element has a unique spectrum, n equals 1, ground state, couch potato state. Okay, then we did the uncertainty principle, and that's it. Thank you.